All right, so back from spring break, we're jumping into 5.6. In 5.4, we learned about two trig functions, their graphs. What were they? Sine and cosine, collectively known as the what family? Sinusoids, the sinusoid family. Those are the only two sinusoids. Those two get their own section, Sahala and Chala. In 5.5, that's what we did the Friday before spring break. That was just an application of sine and cosine, of which there are many. In 5.6, we group the other trig functions together in one section. So that means we're going to cover how many in this section? How many others are there? Not three, at least three, plus the bonus one, because I always like the bonus, 4, right? For a total of how many trig functions? 4 plus 2 is 6. Good. 4 plus 2 is 6. What's 2 plus 4? Also 6. Good. Welcome back from spring break. That is the what property of addition? Commutative. Good. Good. The commutative property of addition. All right, so what we're going to do is we're going to start with the graph of tangent of x. And these are functions, so if you want to write it as f of x equals tangent of x, that's probably maybe a little preferable than just a generic y equals. Now, we have to remember then that if we get rid of our standard notation of theta, that x in this case still represents a what? It's an angle. And we're going to be graphing them in radians. All right, so because it's a function, we like to use x because we're going to be unwrapping the unit circle and looking at what the graph of tangent of x looks like. So if x is an angle in radians, then tangent of x itself, or the function values, represent what? We take tangents of an angle to get a ratio of two of the three sides of the right triangle formed on the unit circle by the angle x. Okay? So you got to be careful. If you're still talking about the definition of tangent from the unit circle, it's probably still beneficial to use theta. What is the definition of tangent in terms of x, y, and r? Y over x. Good. So it measures the vertical aspect of the triangle to the horizontal aspect. Now the x in the definition of tangent and the x behind tangent of x over here, those are different x's, aren't they? They don't mean the same thing. So we're using them in different contexts. All right? So x on the left represents the angle, theta, and the definition on the unit circle is y over x. Now, unlike sine and cosine that had the r in the bottom, those are the only two that have the r in the bottom, you'll notice that all the other trig functions, including tangent, have either x or y in the denominator, which means x and y, unlike r, can actually equal what? Taboo value in the denominator, 0. All right, so we will have discontinuities. So let's go ahead and I'm going to insert a page here. I don't want to just give it away. So let's go ahead and, if you want to insert a page, that's great. Let's go ahead and create a T-chart because we want to unwrap the graph of tangent of x, and we need some values. So just like we did for Sahala and Chala, let's complete the following T-chart. I'll have you complete it. We'll choose some, bless you, random independent variables. I'll choose 0, pi fourths, pi halves, 3 pi fourths, pi, 5 pi fourths, 3 pi halves, 7 pi fourths, and 2 pi. That's once around the unit circle. And if you notice the angles that I chose, of course, the quadrantal angles and all of the pi fourths reference angles. So what I want y'all to do now is just take 1 minute, burn off the dust, whatever, from spring break, and evaluate the tangent at those angles that I wrote down. In other words, complete the T-chart using the unit circle. Oh, yeah. Whew. This could be like a quiz right here. Right? I could quiz you on this, and everyone should make 100. It's kind of a boring quiz because it's just tangent values. The vernal equinox is today. The amount of daylight and non-daylight, which is the opposite of daylight, are roughly the same today. Favorite day of the year. International Day of Happiness. It's also the first day of the last grading period. So it means there's only 10 weeks left of school. Oh my goodness. It's also my daughter's birthday. You're not my daughter. Yeah. All right, let's see how you did. You should be done, right? I'll use green for the vernal equinox. Vernal meaning spring and equinox meaning equal. Daylight and non-daylight hours. That's today. Yeah. All right, so what is tangent of 0? 0. Good. Tangent of pi fourths? Oh, 1. Positive 1. We're in quadrant 1. All right, tangent of pi halves? dne. And remember, it's dne because from the unit circle, it's 1 over 0. And anytime you have a 0 in the denominator, non-zero over 0 means dne. What graphical feature is going to live there? Not a whole. Remember, a whole was 0 over 0. Non-zero over 0 means vertical asymptote because it's some type of infinity. The reciprocal of 0, a very small number, is essentially infinity, or negative infinity, a very big number. 0 and infinity are essentially reciprocals of each other. What's the reciprocal of 0? Plus or minus infinity. What's the reciprocal of infinity? 0. Good. Okay. Got it? All right. 3 pi fourths. What's tangent of 3 pi fourths? Negative 1. Tangent of pi? 0. Tangent of 5 pi fourths? 1. Back to positive 1 because they're both negative. 3 pi halves tangent? dne. Okay, which, again, it's because it's negative 1 over 0. But that still means that there's a vertical asymptote. All right, 7 pi fourths, tangent of. Back to negative 1. And then 2 pi coming full circle on the unit circle, back to 0. So what we have now in this T-chart are a bunch of ordered pairs. And you can probably guess why I chose the pi fourths reference angles when we're dealing with tangent, because we can know their exact value without a calculator. 1 and negative 1. Easy to plot. Let's go ahead and put those ordered pairs down on a graph. So y-axis, x-axis. So just like with sine, let's come out here and call that 2 pi. Half of that would be 1 pi. Half of that would be pi halves. And we get 3 pi halves. So those were the critical values along with 0 for Sahala and Chala. But on this graph, I also chose the pi fourths angles simply because they were nice. And the more points you have, the better the graph is, or the easier it is to connect it. So I'm going to bisect each of those one more time and label them. 1 pi fourths, 2 pi fourths, that'd be 3 pi fourths. 4 pi fourths, there's 5 pi fourths. 6 pi fourths, that would be 7 pi fourths, so on and so forth. And I'll go ahead and throw a couple of these to the left, negative pi fourths and negative pi halves. And then I'm going to come up here and like we did for sine, I'm going to call that 1 and negative 1 because those values also appeared in our T-chart. So what I'm going to do now, I'm not sure what the graph of tangent looks like or if there's even a pattern, but I have now the ordered pairs that can accommodate the points that we chose for the T-chart. So I'll choose green again, and I'll just go ahead and plot the points. All right, so the point 0, 0, that's the origin. So it's going to go there. Pi fourths, comma, 1, that goes there. And then, of course, pi halves tangent was dne, so that's going to manifest as a vertical asymptote. That'll be a dotted line. I'm going to go ahead and put that down also at 3 pi halves. Because in general, when you have vertical asymptotes or horizontal asymptotes, any type of asymptote, and you're sketching a graph, you want to do it first because they kind of define the shape. All right, so now I'll go back to putting my other points. At 3 pi fourths, it was negative 1, so that's down there. Pi was 0. 5 pi fourths was back to 1. 3 pi halves was DNE. 7 pi fourths was -1. And then 2 pi was back to 0. Now, without filling in the T-chart, let's go ahead and add a couple more points. I've labeled negative pi fourths. What is tangent of negative pi fourths? -1. Yeah, because it's coterminal with 7 pi fourths. So I'll put a dot there at negative pi fourths, -1. And what's tangent of negative pi halves? It's coterminal with 3 pi halves, so it's back to DNE. So it's a vertical asymptote. And let's go one more past, or two more past 2 pi. 2 more past 2 pi. If I extend it out, what would be the next critical value if I'm counting by pi fourth? I got 7 pi fourths, 8 pi fourths. This one should be 9 pi fourths. And then 10 pi fourths would be 5 pi halves. Yeah. All right, let's go ahead and fill in those values now. What would tangent of 9 pi fourths be? 1. And tangent of 5 pi halves? DNE. Good. Okay. So now I have enough information, I feel, that I can connect the dots. Now, do I connect the dots with straight lines? No. Remember that the tangent values exist in between the angles that we did not choose through a continuum in between these vertical asymptotes. So vertical asymptotes are very important. They do pull the graph in their direction. So what you're going to do is you're going to take it from the x-axis. I'm going to start at 2 pi, and you're going to draw it going up and to the right. And then from the x-axis, you're going to draw it going down and to the left. And the reason you want to do that maybe as 2 separate sketches, essentially, is because 2 pi ends up being an inflection value. And what happens at an inflection value? The graph changes the direction of its curvature, or just its curvature, the concavity, we say. To the left of 2 pi and to the right of 3 pi halves, we say it's concave down like a frown, so part of a frown. And then to the right, it's concave up like a cup. So you want to exaggerate that inflection value. So we'll just do the kind of the same thing over here. From the x-axis going up and from the x-axis going down, x-axis going up, x-axis going down. And of course, I can keep adding more points. All right, so there is what at least part of the graph of tangent of x looks like. I'll label it up here. F of x equals tangent of x. What is probably the most noticeable feature of that graph compared to, let's say, the graph of sine and cosine? There's no wrong answer. It depends on what you notice. It goes up and down forever and ever. Yeah, good. So where sine and cosine were bounded above and below by 1 and -1, they stayed in between -1 and 1. You're talking about the range of this function, Kroner. What would be the range of this function? -infinity to infinity. Good. You can write it like that. Or you could just say all real numbers. You can use the symbol double bar R. The range is all real numbers. Excellent. So that was most noticeable to Kroner. Anybody else notice anything about this compared to sine and cosine? Last period said, hey, I noticed the vertical asymptotes, which we've already talked about, right? Does sine and cosine have vertical asymptotes? No. We did draw the dotted line as the new y-axis, but these are not new y-axis. These are actual vertical asymptotes. So we have domain restrictions. And as it turns out, sine and cosine are the only two that have domains of all real numbers. And that's why those collectively are the sinusoids. This is not a sinusoid. It has a domain restriction. So let's go ahead and list the domain. What's that? Yeah, the x-intercepts are, what about the intercepts? Well, let's list the domain first, right? The domain is everywhere except where there's a vertical asymptote. And we have a vertical asymptote at pi halves, 3 pi halves, 5 pi halves. The next one would be 7 pi halves, 9 pi halves, 11 pi halves. So you could say it's going to be the set of all x such that x is not equal to odd pi halves. And remember, with set builder notation, you have a little bit of flexibility. Now, that's a great way to remember where the vertical asymptotes are. Odd pi halves. 1 pi halves, 3 pi halves, negative 57 pi halves. That works. But that's not very mathy, is it? So let's do a little bit better than that. The way that you write this, mathy-wise, is to pick any vertical asymptote. And I would always suggest the most convenient one, the first non-negative vertical asymptote, which happens at pi halves. So we'll say, okay, x cannot equal pi halves. And because this function is cyclical and periodic, even though it's not sinusoidal, the vertical asymptotes are going to happen at regular intervals. So you'll say it can't equal pi halves plus multiples of how far apart they are from each other. So how far apart are your vertical asymptotes? How far is it from pi halves to 3 pi halves? Pi, right? 2 pi halves or pi. How far is it from 3 pi halves to 5 pi halves? Also pi. So you'll say it can't equal pi halves plus multiples of pi. Full multiples of pi. So we'll say pi n, where n is what type of number? It can't be a real number. It can't be 1.5. It has to be full increments of pi, like 1 pi, 2 pi, 3 pi, or negative 1 pi, negative 2 pi, negative 3 pi. The integers. Good. And what symbol do we use for the integers? The z. Good. For the integers. So the fact that n could be a negative 1 would then subtract. Pi halves minus pi would be negative pi halves. Well, I don't need to do plus or minus because n is an integer. So like when n is negative 1, I get minus pi. When n is negative 2, I get minus 2 pi. So yeah, if you want to put plus or minus pi n where n is an integer, that's not going to hurt. But the minus is taken into account that n is an integer. So they're pi units away. All right, so we got the domain and range. Those are probably the two first things that you always talk about with any graph. Let's go ahead and look then, since we talked about where the vertical asymptotes are, let's go ahead and state it. The domain is everything but the vertical asymptote, so we actually have vertical asymptotes at x equals pi halves plus pi n, where n is an integer. So if I ask you for the equation of the vertical asymptotes, it would be the same thing that we wrote in the set builder, except this time instead of saying x can equal those, because we're saying those xi's didn't work for the domain, now we're saying x equals those because those are the equations then of those vertical lines. But it's really the same little formula. We also then have inflection values, and I'm going to use that for I. Inflection values. We have those at x equals what? 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. So they're at the whole multiples of pi. Let's go ahead and write it like this. It's going to be at 0 plus pi n, where n is an integer. Or just pi n, because 0 plus pi n is just pi n. Symmetry. Let's talk about symmetry. Does this function have any symmetry? And by symmetry, we're talking about mainly which two types? Origin and y-axis. Remember, origin is your rotational symmetry. If you turn it upside down with your finger on the origin, does it look the same? And y-axis is the folding symmetry along the y-axis. Does this one have y-axis symmetry, folding symmetry? No, it doesn't. That was fun, though. But it doesn't. How about origin symmetry? If you turn it upside down, it looks the same. Yeah. So this function has origin symmetry, which means that it's what? Even, odd, or neither? Odd starts with O, so does ostrich, and the word odd. It's an odd function. And remember what an odd function means in general. It means that f of negative x is the opposite of f of positive x. Opposite x values give you opposite y values. And you can see that clearly from the graph. If you plugged in a pi fourths versus a negative pi fourths, you're going to get opposite y values, 1 and negative 1. So let's go ahead and write that in terms of tangent. That means then that tangent of negative x is the same as the opposite of tangent of positive x. Just like which of the two sinusoids? Which other sinusoid was also odd? Sine. Yeah, sine. Cosine was even. Okay? Every single one of the trig functions is going to have some type of symmetry. Cosine is even, sine is odd, and now we add to the odd list tangent. Okay? Two other features of this graph that I want you to maybe pick up on. The first one, where sine, well, let's look at end behavior. Let's do end behavior. The limit as x goes to infinity of tangent of x. I don't know. We'll see. We'll see. So far, that holds true. So far, the co's are even and the non-co's are odd. We'll see if that holds. What would be the limit as x goes to infinity? As you go out forever and ever to the right, is it going to just go up forever and ever and ever, or down forever and ever, or is it going to taper off towards the value, or is it going to just be anything? If you go out forever and ever, is it predictable what the y values are going to be doing? No. If you go out forever and ever and then take a break and take a pulse of what the y value is, it could literally be any y value between negative infinity or infinity, or it could be a d and e. So guess what the limit is? D and E. The end behavior is D and E. Not by oscillation, just D and E. Same thing for the left end behavior. There's no left or right end behavior. Now, let's talk about what sine and cosine did. Remember, sine and cosine, first of all, were defined everywhere. These have vertical asymptotes. But as you went from left to right, like you do on any graph, sine and cosine went up and then down, then 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 up and then down, and then up and then down, and then down, and then up and then down, and then up and then and down and up, down. Yeah, and we can keep doing that because that's what sine and cosine did. Up and then down and up and then down. Does tangent do that? From left to right, is that what tangent does? I don't know. Let's hop on the graph of tangent like right here. And let's start moving to the right. Tangent's going up and then up and then up. And then you hop on the graph somehow magically on the other side of the vertical asymptote, and it's going what? Up and then up and then up and then up. And then you hop on the other side magically, and it's going up and then up and then up. So is tangent going up and down and up and down? No, it's going up and 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 up, wherever it's defined. So that's not up and down. So for a function that does that, we say that it is monotonic. No. Monotonic. Or we sometimes use the word strictly. Monotonic, or strictly, in this case, increasing over its domain, which we've already established what that is. So wherever this graph exists, from left to right, it's doing one thing and one thing only. It's going uphill. So we say it's monotonic increasing or strictly increasing. They're interchangeable over its domain. Now, is this function also one-to-one? The last time we saw a strictly monotonic increasing function was ln of x, or e to the x. They were one-to-one, so they were inverses of each other. Is this function one-to-one? A function that's one-to-one has to pass not only the vertical asymptote test or the vertical line test, but the horizontal line test. Does this one pass the horizontal line test? Fail, 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 fail. No, it fails. It fails. Miserably, right? For any y value, how many x values are associated with it? Infinitely many. Ooh. That y value gets around. Okay? That y value gets around. The x's are faithful to the y values. The y values, Okay? So this is one of those special cases where we have a function that's monotonic increasing, but it's not one-to-one. And the reason that happens is because of the vertical asymptotes. Okay? Now, the perhaps most important thing here is the fact that tangent does repeat itself at regular intervals, just like sine and cosine. It's not a sinusoid, but it is a periodic function. So my question to you is then, what is the length of one cycle? That is, what is the period of this function? If I were to make a stamp, so I could just stand on the assembly line and have this graph come by on the x-axis, I could just sit there and go stamp, 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 and make the graph of tangent. How wide would my stamp need to be, x-wise? How many radians does this graph repeat itself? Well, let's see. I have a vertical asymptote, and then I have what looks kind of like the x-cubed graph, the disco graph. Okay, except it's hemmed in between the vertical asymptotes. And then I have another vertical asymptote. And then, deja vu, I've got another little x-cubed looking graph. And then a vertical asymptote. And then another x-cubed looking graph. So it looks like one cycle of tangent would be between vertical asymptotes, right? Because between the next set of vertical asymptotes, the graph repeats itself. So that should be one cycle, right there. One cycle between vertical asymptotes. How far is it between vertical asymptotes? Pi. So guess what the period is? Pi. And that's different than sine or cosine. What was the period for sine or cosine? 2 pi. It was axis high, axis low, axis. Here, it goes axis, vertical asymptote. Axis, vertical asymptote. Axis, vertical asymptote. And it repeats itself every axis point or every vertical asymptote. So once around the unit circle completes 2 cycles of tangent instead of just 1. So that is a noticeable difference between sine and cosine. Aside from the discontinuities and the range, is that the period is pi. Tangent's period is pi. It repeats itself every pi radians. So the distance between vertical asymptotes. So here's your new parent function, tangent of x. And if you want to remember it, like the Sahala-Chala method, T for tangent, also for Texas and Tennessee. Okay. We start on the y-axis with an inflection value. So I'm going to put I for inflection value. And the next critical value is not pi fourths. We don't need the 1 there to sketch the graph. The most important feature then that comes after that is the vertical asymptote. So we put vertical asymptote. And the next critical value, which you're already into the next cycle, would be another inflection value, and then another vertical asymptote. So TIV is all you need to sketch one cycle of tangent. If you want to add IV to the end, to viv, to vivi, to vivi-viv, whatever, you don't need that. One cycle is just TIV. All right? And the period is pi. So sine and cosine counted by quarter cycle intervals. Tangent, we only need to count by half cycle intervals. We count by half cycles. And in between any 2 critical values then, which are a half of the period away from each other, it's going to alternate inflection value, vertical asymptote, inflection value, vertical asymptote. So you only need 3 critical values for one cycle instead of the 5. And you count by half cycles instead of quarter cycles. So in the future then, if I ask you to quickly then sketch your parent function f of x equals tangent of x, here's what you're quickly going to do. Y-axis, x-axis, you're going to say, okay, pi halves, pi, 0, negative pi halves, negative pi, and you're going to put vertical asymptotes or inflection value at 0, vertical asymptote at pi halves. And once you have one of the 2 critical values, If you know that tangent passes to the origin, that helps as well. Then it's just going to alternate. Inflection value, vertical asymptote. Inflection value, vertical asymptote. Okay, so this would be a vertical asymptote and another inflection value. And then you just have to remember that tangent is monotonic what? Increasing. So there would be 2 cycles of tangent. The main branch or the main cycle falls between negative pi halves and pi halves. And then we have 2 half cycles on either side. All right? So there's your parent function, TIV, tangent. Questions on tangent? Okay. Let's go ahead and do something different now. Let's meet a new parent function. And let's call it, there's 3 left. What do you want to meet next? Cotangent, yeah. Let's go ahead and meet cotangent, because we met sine and then cosine. Let's meet tangent, and then it's, what does the co stand for again? I forgot. It's been a long time. Co-function, all right, complementary function. Cotangent. All right, so I'm going to leave tangent there in green. And in red, I'm going to sketch g of x, just to give it a different name. I'm going to sketch cotangent of x. Now, I'm going to sketch it on the same graph. So if you want to just copy tangent, here's how we're going to sketch cotangent. We could do it the same way we did tangent. We can make a T-chart, pick some nice angles, and then plot the points. But I'm going to sketch cotangent by using the graph of tangent, because I know that cotangent is just the what of tangent? Reciprocal. Good. It's the reciprocal. So if I have the tangent's y values, all I have to do to get the cotangent's y values are, at each of the x values, graph the reciprocal of the y value that I have shown. That's pretty easy. I think so. So here we go. Let's start with the easiest values to flip, which I think are the x-axis values. Because what are the tangent values on the x-axis? 0. So wherever tangent is 0, cotangent is going to be the reciprocal of 0. And what is the reciprocal of 0? Not 0. Thank you, infinity. Because 0, remember, is really 0 over 1, or 0 over 5, or 0 over negative 3. When you flip that, you get 1 over 0, or negative 3 over 0. And that is some type of infinity, which means vertical asymptote on the graph. So again, what's the reciprocal of 0? Infinity. What's the reciprocal of infinity? 0. So everywhere tangent has an x-intercept, cotangent's going to have a, guess what? Vertical asymptote. Wherever tangent has an x-intercept, cotangent has a vertical asymptote. There's going to be a lot of information on here. That's why we're using a contrasting color. And by the same argument, then, wherever tangent has a vertical asymptote, which is some type of infinity, cotangent is going to have the reciprocal of infinity, which is what? 0. So everywhere tangent has a vertical asymptote, cotangent's going to have an x-intercept, or an inflection value. So they just kind of interchange characteristics. The vertical asymptotes of tangent are the inflection values of cotangent, and vice versa. Now, because we have the pi-fourths angles plotted on this graph, we can flip those values as well. So come over here to the tangent value in green at pi-fourths. What was tangent of pi-fourths? It was 1. So cotangent of pi-fourths should be the reciprocal of 1. What's the reciprocal of 1? 1, because 1 is like 1 over 1. And when you flip 1 over 1, you get 1 over 1, which is still 1. Cotangent of pi-fourths and tangent of pi-fourths are the same. So that is going to be a point, a common point on both graphs. So I'm going to highlight that point, pi-fourths 1, in red. And then I'll do the same for the others. 5 pi-fourths and 9 pi-fourths. And what happens at the negative ones? What's the reciprocal of negative 1? Also negative 1, because negative 1 is the same as negative 1 over 1, which when you flip it is 1 over negative 1, which is still negative 1. In other words, tangent and cotangent at all your pi fourths are the same value. So at negative pi fourths negative 1, 3 pi fourths negative 1, 7 pi fourths negative 1, those are also going to become red values. And now all I have to do is connect the red dots in between the red vertical asymptotes in much the same way we did tangent. All right? So if you do that, start from your axis points and go both ways. So I'm going to start at negative pi halves. It looks like it's going to be decreasing. Decreasing from 0 to pi halves. Inflection value, pi halves to pi. Same thing here. I'll be decreasing to 3 pi halves. And then decreasing from 3 pi halves to 2 pi. And you want to kind of exaggerate the curvature change on the axis points. There then is the graph of cotangent from the graph of tangent. Now, to make it a little bit easier to see, let's right below there just draw it by itself, so you don't have the obscuring green lines. So notice that it has a vertical asymptote at 0, whereas tangent has an inflection value. Its next vertical asymptote is at pi, and then at 2 pi. So it has vertical asymptotes where tangent had inflection values. And it has, at the odd pi halves, it has inflection values, which is where tangent had its vertical asymptotes. And then the other remarkable feature that's different is that it's decreasing. And tangent was what? Increasing. So there is a better view then of the graph of cotangent of x. All right, let's talk about the same things we did for tangent, for cotangent. First thing was domain. What's the domain of cotangent? Well, it's everywhere except the vertical asymptotes, right? Which are now at whole pi's. So again, the set of all x, such that x is not equal to 0 is the first non-negative vertical asymptote, plus how often they occur, which is pi n, where n is an integer. So you could either leave it as 0 plus pi n, or just pi n in this case. Remember, those were the inflection values of tangent. What's the range of cotangent? All real numbers. That's the same as tangent. Then we looked up here. Let's do the vertical asymptotes. This one has vertical asymptotes now at x equals pi n, where n is an integer instead of x does not equal. And the inflection values. The inflection values are at the odd pi halves, which are going to be at x equals pi halves plus pi n, where n is an integer. So once again, it looks like everything is opposite. They trade places. The next thing we had was a symmetry. Does tangent look like it has any symmetry? Even, odd, or neither? Origin, y-axis, or neither? Take your iPad and turn it upside down. Does it look the same? Mine does. Does yours? It also has origin symmetry. Origin symmetry. So it's also an odd function. So that means cotangent of negative x equals the opposite of cotangent of positive x. So Trevor, is every single function that's going to be even? No. So far, of the 4 we've learned, they've all been odd except cosine. Cosine has been even, the only one that's been even. The next thing we looked at was end behavior. What is the end behavior for this one? The limit as x goes to either infinity or negative infinity? Yeah, D and E, by the same reason. The y values could be anything, literally anything, including nothing. It could be D and E. Monotonic, is it monotonic? Yeah, it's monotonic what? Or strictly what? Decreasing over its domain, which is not all real numbers, so it's not 1 to 1. And what's the period? What's the smallest distance it takes to repeat itself? Still pi. Good. So tangent and cotangent, unlike sine and cosine, have discontinuities, and their period is pi instead of 2 pi. Now notice the co in tangent and cotangent means complementary, as we already said today, and complementary angles again add up to how many degrees? 90, or how many radians? Pi halves. So just like sine and cosine differed by pi halves radians, tangent and cotangent also differ by pi halves radians. If you took the graph of tangent and pick it up and move it over pi halves and set it back down, now the vertical asymptotes and the inflection values will coincide. Same thing with cotangent. If you pick it up and move it over pi halves units, the vertical asymptotes and inflection values will coincide with tangent. Now there's one other thing. One becomes increasing and one becomes decreasing. But aside from that, they only differ by pi halves radians. And that's why they are co-functions or complementary functions. All right, so to memorize this parent function, which is the last thing we'll do, cotangent, we got to reuse C if you want to use that method, because we've already used C for cosine. But for cotangent, it could be, it starts where? On the y-axis, we start with a what? A vertical asymptote. And then it goes inflection value. So CVI. Is that a pharmacy somewhere? I'm not sure. CVI. Or if you want to make the distinction between cosine, cot V, I don't care. I don't really use cot V and tiv for tangent and cotangent. I just remember tangent passes through the origin, so it starts at 0. Cotangent is undefined at 0, so it starts with the vertical asymptote. But just like tangent, you're going to count by half cycle intervals, and they just alternate. Inflection value, vertical asymptote. Inflection value, vertical asymptote. So as long as you know where it starts, that's all you really need, because the other one then is just going to be the opposite, the vertical asymptote or inflection value. Tangent starts at 0. Cotangent starts at a vertical asymptote. You got 2 new parent functions. Guess what we're going to do tomorrow? Well, we're going to learn the other 2, but first we're going to sketch transformations of cotangent and tangent. And then we'll learn the other 2, which are, I forget their names, secant and cosecant. 5.5, if you weren't here the Friday before spring break, we'll just make that due by the end of the week. We're skipping 5.5, but there's one assignment that's on my school website. And I'd be happy to show that to you if you haven't found it yet. All right, we're done for the day. Have a great, fantastic rest of the day.